Okay, let's get started. So last time we talked about the smoothing technique. Okay. The general idea is that for many non-smooth problems, previously we were using this subgradient method. So the subgradient method has this complexity, 1 over epsilon squared. This complexity is very high if we want to achieve a small accuracy. But in contrast, if the problem is smooth, then we can do accelerated gradient descent. Okay. And for accelerated gradient descent, the convergence complexity is very low, 1 over square root of epsilon. So the idea is that can we smooth the non-smooth problem and then apply this accelerated gradient methods to solve the approximated problem. So that is the motivation to define this smoothing idea. And then we introduce this alpha beta smoothable function. So we say a convex function is alpha beta smoothable if the following two conditions are satisfied. For the first condition, we assume that we can find a approximate convex function f mu. For this convex function, it is a lower bound of f and it is an upper bound. And f is also upper bounded by this f mu subject to some constants. So basically, the original function, the original problem fx, is bounded between these two approximated functions. And in the second condition, we require that this approximated function f mu is a smooth function. In particular, it is alpha over mu smooth. So you can see there's a trade-off between approximation accuracy and smoothness. If we want a very high approximation accuracy, then this mu would be very small. But on the other hand, the smoothness parameter will be very big. And we know that in the gradient descent, when this smoothness parameter is huge, the condition number can be very big. That makes the problem ill conditioned, very hard to solve. Right? So in general, we need to choose a proper value of mu to balance between these two. And the general idea of smoothing is basically, we have seen some specific examples to illustrate this smoothing idea. For example, for this L1 norm function, basically the absolute value function in the one-dimensional case, the way we smooth it is basically replace this sharp L1 absolute value linear function by a smoothed quadratic function. Okay. And this is called the Huber function. So when z is close to 0 between negative mu and mu, the function behaves like a quadratic function. And then outside this region, the function behaves like a linear function. So for this h mu function, we can show that it provides a mu over 2 approximation of the original function, and also it is 1 over mu smooth. Okay, so this is a very nice example to illustrate this smoothing idea. And then we can further smooth functions in the high dimensional space. For this L2 norm function, it is not differentiable at the original point, but we can smooth it. Like by adding some constants and taking square root. And also for the pointwise maximum function, for the maximum function, we can also smooth it by this function. This is called the log sum exponential function. Okay. And moreover, the smoothing idea can be can satisfy some very simple computational rules like additive rule or the multiplicative rule. So basically, once you consider two different smooth approximations of two functions, then their linear combination is also a smooth approximation of the linear combination of these two functions. And the smoothing parameters will be scaled correspondingly by this linear combination. And we also have this, last time we also discussed this affine transformation rule. So basically, with an affine transformation, the smoothing parameter will be scaled by, in particular, the alpha part will be scaled by the spectral norm of this transformation matrix. So let's go to the So today we are going to formalize this idea of smoothing using this so-called moral envelope definition. So this moral envelope, so sometimes we call it the Morrow-Yosida regularization. This is a technique to construct smooth functions in a systematic way. So specifically, the moral envelope of a convex function f with parameter mu is defined as follows. So let's first look at this definition, and then we will discuss its relation to the proximal mapping. Okay. So intuitively, okay, if you want to smooth a function f with a certain parameter mu, then we can consider this moral envelope. So this capital M stands for the moral envelope. And we are looking at the mu f. Yeah, mu times f. Okay. So first of all, this is a function. This moral envelope is a function of x. It's similar to fx. It is also a function. But the way we define this function is based on the parameter mu and based on the function, the given function, given convex function f. Okay, so how do we define this value, this moral envelope value at x? It is defined as, here, look at this optimization problem. And then I consider the infimum value. So I take infimum over z. Okay, you can understand it's a minimum value. So this x is given. X is here. X is a fixed, is the input parameter. Given x, we can consider such an optimization problem. Fz plus this quadratic term. Now, this quadratic term is scaled by this parameter mu in the denominator. And then this is a given x. This is an optimization problem over z. So then we search over all the z's, and then the infimum value of this problem over z is set as the value of this moral envelope. Okay. See, the left-hand side, we have the moral envelope evaluated at parameter x. So this is a certain function evaluated at x. So the left-hand side corresponds to a certain number, right? So this number is defined by the right-hand side. It is given this x, we construct this optimization problem. And then I'm looking at the infimum value of this problem. The infimum value is assigned to the value of this moral envelope. Okay. So the right-hand side is something belongs to a real number. The right-hand side is a real number, and this number is the value of this moral envelope. Now this is very different, slightly different. I would say it looks similar, but very different from the proximal mapping that we introduced before. So for the proximal mapping, everything looks the same except that here we're looking at the minimizer, not the infimum value. Okay. We're looking at the argmin, the minimizer of this problem. That minimizer is the output of this proximal mapping, right? So here we are creating something in the parameter space. It's not a value. But proximal mapping, the moral envelope is the infimum value that we achieved. Okay, so these two, they are related. They are highly related, but one is defined by its infimum value, one is defined by the minimizer. So they are different operations. Okay. So any questions? So the moral envelope is a function. Input is the x, output is a value, it's the infimum value of that optimization problem. The proximal mapping input is x, output is another variable defined as the minimizer of this problem. Okay, these two are different. And we will see that this moral envelope function, this moral envelope is a smooth or regularized form of f. So once we define the function in this way, it automatically creates a smooth version, a smooth approximation of the original function f. Okay. And this slide shows the connection between the moral envelope and the proximal operator. Like we just explained, proximal mapping is the minimizer of this problem, right? And moral envelope is the infimum value of the same problem. So you can say that just by these definitions, the proximal mapping, basically this point is the minimizer of that problem involved in the moral envelope. So this point achieves the infimum value of this problem. Therefore, we can simply plug in this minimizer into that problem, and then we can obtain an exact expression for the moral envelope. So the moral envelope, now here is the infimum value, but by definition of the proximal mapping, this is defined as the minimizer of this problem. Therefore, if we plug this minimizer into that problem, we automatically achieve the infimum value. So basically, the infimum value equals f evaluated at this minimizer. So I simply plug in this minimizer. We just substitute z with this proximal mapping. So, and then we will achieve that infimum value. So this is an equality. If you can get that proximal mapping, plug it inside, you get the infimum value of the moral envelope. Okay, that's why we have this equality. It looks complicated, but the essential idea is, by definition, the proximal mapping, that mapping is defined as the minimizer. So once you plug it in, you automatically achieve the infimum value. Okay. And a very, very interesting property is that this function is differentiable. Let's go back to this function. The way we construct this moral envelope, this function is differentiable. Even though the original function f may not be differentiable. For example, if f is the L1 norm, then this moral envelope of L1 norm is differentiable. So this function is always differentiable. And the derivative, the gradient, is given by this formula. This x minus the proximal mapping over mu. A very, very simple formula for calculating the gradient of this moral envelope. Or we can rearrange this equation and solve for the proximal mapping. So we get another equation. The proximal mapping can also be characterized as performing one gradient descent on the moral envelope as x minus mu times the gradient of the moral envelope function. Therefore, these two, they are highly related to each other. The proximal mapping talks about the minimizer. Moral envelope talks about the function that the infimum function value that it achieves. And here are the fundamental key properties of this moral envelope function. So again, this is an abstract construction, right? Because the way we construct this function is based on the Feynman value of this optimization problem. So it is not a explicit formula. So you will have to work out this Feynman value in practice, case by case, once we are given the function of f, once we are given a specific function of f. However, with this abstract construction, we are guaranteed to have several desired properties. First of all, this function, this moral envelope, is a convex function. But intuitively, inside, f is convex. This is strongly convex. So we are taking pointwise Feynman over strongly convex functions. So it is guaranteed to be convex. We have some basic rules to guarantee that. And moreover, as we just mentioned, this moral envelope function is differentiable. This is the gradient, it's differentiable. And moreover, this gradient is Lipschitz continuous. So this is a 1/μ smooth function. Okay, it is a smooth function, which means the gradient is 1/μ Lipschitz continuous. So it's a convex function. It's a convex and a smooth approximation of the original function. So the last bullet points summarizes this idea. So if the function f is convex and LF Lipschitz, if the function is LF Lipschitz, then this moral envelope is a 1/μ smooth approximation of the function. And the approximation parameters are 1 and the LF square over 2. Okay, so this is the alpha, 1 is the alpha, and this is the beta parameters. Therefore, this moral envelope function provides a systematic way to construct smooth approximations for convex Lipschitz functions. Right? As long as f is Lipschitz and convex, the moral envelope always satisfy these three conditions. And these three conditions basically shows that this envelope is a good it's a smooth approximation of the original problem f. So let's look at this, the proof of this, the last bullet point. Let's show that this function is indeed a smooth approximation of function f. So first of all, we claim that the moral envelope is a lower bound of your original function. Why is that? Because the moral envelope is defined as the Feynman value over z. Well, because it's the Feynman value over z, therefore, right, this is is defined as the Feynman of this problem. So I can set z as x, and that will be at least greater than or equal to this Feynman value. So it will be less than or equal to replacing z by a specific parameter, for example, x. right? So because the moral envelope is defined as the infimum over z, meaning that it is the infimum value over all possible choices of z. So if I replace z by x, which is a specific choice, that will be at least bigger than or equal to this infimum value. So therefore, I claim that this one is less than or equal to the right-hand side. Well, I replaced z by x. And this is simply fx. Right. Therefore, we can see the moral envelope is always the lower bound of your original problem. Right? It's always a lower bound. And then we can also look at this difference. Okay, so let me go back to the. Okay, so basically we need to check these conditions. Right? We just show that moral envelope is a lower bound of the original problem. Then we need to show that it is also smooth. It's also we also need to show that we need to also demonstrate the upper bound, right? So fx less than equal to the upper bound. Okay. So how do we show that? This part, this is the inequality for the upper bound. If you rearrange this inequality, right? So you will have fx, if we move it to the right-hand side, fx less than equal to the moral envelope plus a constant, right? So this serves as the upper bound. But how do we prove this inequality? Well, for the upper bound, we need to calculate the difference between these two functions, right? This is the moral envelope, our approximation, minus the original function. Okay. Now look at this difference. I writing down the definition of moral envelope. The moral envelope is the infimum of this problem. And we can put negative fx inside because here we are infimum over z. Fx is a constant. Fx does not depend on z, it's a constant. We can put it inside. It does not affect the infimum value. It does not affect the choice of z. Right. Now, because f is a convex function, so this difference by convexity of f can be lower bounded by this inner product, just by convexity. Well, gx is a sub-differential of f and x. Sub-differential. And then look at this problem. This is a infimum over z. Well, inside is a linear. The first one is a linear term in z. Right? Gx is constant, x is constant. Only z is the parameter. But the first one is a linear term. Linear term plus a quadratic term. We can actually analytically solve this problem. This is like a quadratic optimization problem. So to solve it, turns out that this is the minimum value. I think the minimum is achieved when z minus x equals to gx, equals to negative gx. But basically we can solve this quadratic optimization problem and get this minimum value. And because F is L Lipschitz, so we know that the subgradient are bounded by LF. The L2 norm of the subgradient are bounded by LF. Therefore, this term is further lower bounded by replacing these terms by LF squared. This provides an upper bound for the smooth approximation. So here we conclude that Fx is less than equal to the moral envelope plus this constant. Okay. So this is the other side, the upper bound. And moreover, given that the moral envelope is smooth and is a convex and 1/mu smooth function, right? Putting everything together, we can claim that this MF, this moral envelope, is 1/mu smooth approximation with these two parameters. Okay. So alpha equals to 1, beta equals to this one. Right? So we have checked all the three conditions: lower bound, upper bound, smoothness. So this proves this claim. Even these two, we have proved the last bullet point. So therefore, this is a systematic way to construct smooth approximations of Lipschitz and convex functions. In fact, it is also the essential idea for the proximal gradient algorithm. And we can also do the smoothing via conjugation. We haven't formally introduced the conjugation idea, but I think we can actually introduce this idea starting from here. So given a function g, we define f to be the conjugate of g. This star means conjugate. G star is the conjugate of g. We define the function f as the conjugate function of g. Now, what does this precisely mean? Okay. This precisely means that this is how this conjugate function is defined. Okay. So we have a gx, right? We have one function, gx. Now let's look at fx, which is defined as the conjugate of gx. G conjugate, g star. Fx is defined as the conjugate function of g. Now this is defined as the supreme value of this optimization problem. Again, this definition is abstract. It is not explicit form, but the idea is like given the input x, fix this x, and this x is fixed in this inner product, and then we look at this optimization problem. It's a linear term in z, minus g of z, right? And we can then the supreme value of this problem over z is defined as the value of the conjugate function. So this is the definition. This is a definition of conjugate functions. So one can build a smooth approximation of f by adding a strongly convex component to its dual. Basically, if fx is defined in this way, if fx is the conjugate of a certain function g, then we can immediately build a smooth approximation f mu x simply by adding an extra term in this optimization problem. And as long as this d of z, the extra term, the extra function that we added to this problem, as long as it is strongly convex, then we can show that it satisfies some smoothness properties. So we add this negative mu times d of z function to the conjugate function. And here assume that this d is one strongly convex and continuous. And following this notation, see that everything except for this linear term will be denoted as the conjugate function, right? So here's a linear term minus g of z. So this entire function is denoted as g star, right? It's always this guy with a star on top of it. And here is the same thing. Now it becomes g of z minus mu times d of z. Therefore, following this convention, the entire supremum is denoted as g plus mu times d to the conjugate of x. So you view this entire term as one function. The function we are looking at is g plus mu d. So this f mu x is the conjugate of this perturbed function. It's g plus mu times d. So if you compare these two, our original function is the conjugate of a certain function g. And then how do we do the smoothing? Well, we simply perturb g by a small function, mu times d. This mu controls the perturbation scale. You can control the mu parameter mu. By adding a little bit strongly convex function d to this g function, and then take the conjugation, we can show that this f mu is a smooth approximation of the original function f. And there are some properties. First of all, G plus mu D is mu strongly convex. Why? Because G is convex. We assume G is convex. D is one strongly convex. So mu times D is mu strongly convex. Right? The convex function plus mu strongly convex function is mu strongly convex. Oh. Now this function is mu strongly convex. And there are some fundamental results to say that if this function is mu strongly convex, then its conjugate is 1 over mu smooth. Okay, the conjugate function is 1 over mu smooth. And also, we can also have this property. The fx is bounded between the smooth function f mu x. Well, the upper bound depends on mu times capital D. Well, capital D is the supremum of this dx. Okay. So in the end, we can conclude that this f mu is also a smooth approximation of the f function with parameters 1 and d. Okay. So this smoothing is by adding a strongly convex component to the conjugate function. By perturbing the conjugate function, we can smooth the function. This also shows that smoothing is fundamentally connected to conjugation. And conjugation is a very important transform in optimization. Okay, now let's look at some examples of how to smooth functions using the conjugation. So, for example, I want to smooth this absolute value function. Here we will smooth this function through the conjugation approach. First of all, notice that the absolute value function can be written in such a form. You can check it by yourself. It's a supremum of z times x over all the z's whose magnitude is smaller than 1. You can check this by yourself. It's one dimension. It's not hard to observe that. And therefore, this falls into the conjugation definition. But if you compare this with this definition, we have z times x is one dimensional, so this inner product becomes z times x. Now, what about this negative g of z? This negative g of z actually corresponds to this constraint. As we mentioned before, we can put this constraint into the objective function by introducing the indicator function. So that g of z is basically an indicator function. Okay, so S value is basically sup zx minus the indicator. If this indicator holds, it's 1. sorry, if this indicator holds, then it's zero. Otherwise, if this condition is violated, it is infinity. Infinity. Okay. Therefore, the absolute value of x can be viewed as the conjugate function of an indicator function. The conjugate of this indicator function. So this is our GZ. So there's a connection, very close connection among all these functions. Indicator function is connected to absolute value function through this conjugation. So this is our f, right? And this right-hand side is the conjugate of gx. The entire thing is the conjugate function of g and evaluated at x. Therefore, we observe that the absolute value function is essentially the conjugate function or the conjugate of this indicator function. And then we can add a small perturbation to this conjugate form. We introduce a small, so this perturbation dz we use is the quadratic, very simple quadratic function. So we add a little bit quadratic function to this conjugation. If you solve this problem, again, it's a one-dimensional problem. One-dimensional quadratic function over a bounded domain. We can do this calculations, calculate this supreme value. You can get this result, which is exactly the Hoover function that we introduced before. With between negative mu and mu is quadratic. Outside this region is linear. Okay. So this is exactly the Hoover function. Right. So actually, all the previous examples that we have looked at, they are all derived in this way, through this Morrow envelope or through this conjugation. So this is another standard way to build smooth approximations. You write your function as a conjugate of another function, and then perturb that function a little bit. You will get a smooth version. It's a very interesting idea. So you can say that essentially the conjugation, this transform, will translate strong convexity into smoothness. This so adding a little bit strong convex term to the conjugate function will lead to a smooth version of the objective function in the conjugate space. Okay, so these two are deeply connected. And this is another way to rewrite. Well, see, this is the one way to write down the absolute value. Okay. This is another way. You can check. Again, it's one-dimensional, so supremum over z1 minus z2 times x. Well, z1, z2, what? z1, z2, they must form a like a probability mass function. They are positive, sum up to 1. So Z1 and Z2 are on the probability simplex. And you can also check that the supreme value you can achieve is absolute value of x. Okay. Another interesting observation. And therefore, this is again another form of communication, because this is again a linear term. Z1 minus Z2 times x is a linear term. So we can also perturb this form by introducing this dz function. Here we are using it's kind of like an entropy function. So z1 log z1 plus z2 log z2 plus log 2. This is like a entropy function. So adding mu times dz to the supreme problem, okay? And then we can solve this problem. Again, everything is scalar, z1, z2, we can take. Yeah, it's not that easy to solve this problem, but in the end, we can get an analytical form. So it turns out that by adding this dz to this supreme form and solve that problem, we get a smooth approximation. So the smooth function takes this form: f mu x equals to mu times log cosine h x over mu. And so this is very different from the smooth construction that we built here. So you can see that in the first case, the Huber approximation is basically it's kind of divided into two different parts. One is quadratic, one is linear, so they are very different. But here we put everything in a single function. And this function, when x is close to 0, it is differentiable, but it's very sharp. When x is big, this function behaves like a linear function. Because we have log, we have exponential, they will cancel out. Okay. So this is a very interesting idea to approximate the absolute value. Yeah. Moreover, more generally, consider the norm of any vector x. Consider this norm function. And we know that the norm can be characterized in this variational form. It's the supremum of this inner product, while the supremum is taken over z. It's considering all the z's whose dual norm is less than 1. This norm star corresponds to the dual norm of z, right? For example, L1 norm, then the dual norm is L infinity norm. L2 norm, the dual norm is itself. Right? So therefore, the norm can also be written in a conjugate form. And then we can simply smooth the norm by introducing, by adding this mu times d of z to this conjugate form. Okay, so this is a standard way to smooth all the norm functions. For example, in the previous examples, we have this example, right? We have this L2 norm function, and we directly claim that this f mu is a smooth version of this. But how do people construct this f mu function? Well, just by following that idea. Following this idea, you set, now you pick L2 norm. You pick L2 norm. So this dual norm will be itself. So L2 norm is supremum of Z X supremum over Z whose L2 norm are less than 1. So L2 is the dual of itself. And then you add some perturbations. Here we can simply define this dz by the L2 norm square. You can and then you solve this problem. You solve this problem. And you will get that answer. So this is a quadratic problem, so you can so obviously, okay, how to solve this problem? Let's see. So obviously, in order to make, we are taking supremum over Z, right? So now look at these two places that involve Z. The first place is the inner product between Z and X. So intuitively, it is better to make Z exactly aligned with X. So this inner product will achieve the maximum value. But at the same time, we need to make sure Z is not that is the length of Z is not too big. So we need to balance these two terms. So what we can do is introduce. So we know the supremum value will be achieved by Z equals to delta X. Because based on the first inner product term, when Z is aligned with X, the first inner product term will achieve the maximum value, regardless of the norm of Z. Assuming if you consider all the Z's with the same L2 norm, then this one would always give us the highest supremum value. So this delta should be between 1 over X in order to make sure Z, L2 norm of Z is less than 1. Right. Okay. And now this problem becomes supremum of Zx now becomes delta X square minus mu over 2 Z square. While this delta is between this. Okay. And I think from there you can get the supremum value. But now it is a one-dimensional product over delta. Yeah. So solve this problem. I think you will get that approximation that we have seen in the previous slides. Okay. Yeah, I think I will stop right here. So for the next part, we'll start to talk about how, okay, now we have some systematic way to smooth these non-smooth functions. For example, for example, this is a non-smooth function. We can only apply subgradient method to optimize it, but subgradient method is very slow. So what we do is we first smooth it so that we can apply better algorithms. Okay, once we smooth it to this f mu, now it is convex, smooth. Okay, we can apply accelerated gradient methods to solve it. Very nice. But then there's a trade-off. On one hand, the optimization algorithm converges faster because it's now the problem is nicer. It's a smooth problem. You can get accelerated convergence. But on the other hand, if you make it too smooth, this function will be very different from the original function. So there will be an approximation error. Right? So it's like you are applying a faster algorithm to solve a approximated problem. Right? So maybe you will converge to the solution of this approximated problem faster, but this solution might be different from the solution of your original problem. So there's an approximation error between these two. So we have to consider, we have to put everything together and see overall if it is beneficial to apply accelerated algorithm to the approximated problem compared with applying the subgradient method to the original problem. So there's that approximation optimization trade-off. Okay. But for the smoothing, basically, these are the two systematic approaches. One is moral envelope. This approach is useful when we deal with functions that do not have much structures. If you randomly give me a function, maybe I will just consider it moral envelope. But if the function that you give me, fx, can be written as a conjugate of another function, right? And this is indeed the case for many functions, especially for norms. In this case, we can do smoothing in a very simple way. We simply add a perturbation, a strongly convex term to this conjugate form, and this will automatically give us a smooth function. It's a very nice idea. And we have seen that for the absolute value function, we have at least two different ways to construct this conjugate function, and then they will lead to different approximations. They're very interesting. These are very interesting approximation ideas. Okay, so I think I will stop here, and for next lecture, we'll talk about the algorithm and the convergence analysis for the smooth problems. And I think we don't have a homework associated with this one. So you can spend more time to work on homeworks 5 and 6. See, what is homework 7? Homework 7, you can spend more time on homework 7. That is about accelerated gradient methods. Okay. I will see you guys on Thursday.